the Arrhenius equation in the kinetic molecular theory and this section on rates of reaction relates rate constants, rate of reaction, activation energy, and temperature factors. That relate to specific types of reactions. It is derived from an Arrhenius equation that defines rates of reaction as a function of probability factors, the CENT factors that we drew in the Maxwell-Boltzmann distribution curves. Well, I'm not going to ask you to derive this thing, so I'm just going to give you the equation, and you will need to learn this equation and apply it when the time comes. I've got a couple of problems. We will work on this, but it is simply the natural log of the ratio of rate constants for a given reaction. If you use two different temperatures, you'd have two different rates, which would translate to two different K values. And this is equal to the activation energy over the thermodynamic R value. I'll write that out here in a minute. And is related to the ratio T temperature, Kelvin temperature, 2 minus temperature 1. And that's divided by T1 times T2 temperatures. And so that's the Arrhenius equation. Now, in using this, you can see the next problems, the next two problems that will work. So I want to relate it to the problem to the equation, so you'll see how it's pretty much applied. In a series of experiments on the decomposition of dinitrogen penoxide, rate constants were determined at two different temperatures. At 35 degrees, it was found to be 1.4 times 10 to the minus 4 per second, and at 45, 10 degree increase, the rate constant was 5 times 10 to the minus 4. What's the activation energy? So it's giving you the K1 and K2 at T1 and T2. And so our value, I'll just jot that in here, in the gas laws is 0.08206. Now this is on your reference sheet attached to your exam, and so you don't have to memorize this, but it's 8.314 joules per mole Kelvin, which translates into what you'll use in the equation is actually the kilojoule form, which is 0.008314 kilojoules per mole Kelvin. So that's the constant that you would use in that position right there. So you have K1, K2, T1, T2, and R, and so you just simply solve for the delta E in this problem. So let me jot down K1 is equal to 1.4 times 10 to the minus 4 seconds to the minus 1 at 35 degrees C, and K2, and when we convert that to Kelvin, is 5.0 times 10 to the minus 4 seconds to the minus 1 at 45 degrees C, just to be sure. And so we'll put in those temperature values in terms of Kelvin, and then solve for the delta E value. Put them activation energy in there. So what we're looking at is ln of K2, which is 5 times 10 to the minus 4 per second, which will cancel with the seconds in this K1 minus 4. And that's equal to delta E activation over 0.008314. And then T2 would be 318 minus 308 divided by 308 times 318. So it's really just a plug and chug type problem. And so I would suggest kind of simplifying, or however you want to approach it from there. Anyway, solving for the delta E sub A, and it will be in kilojoules, so that'd be 1.273 over 0.0122 kilojoules per mole, actually. And looks like 100 and I get 104. I think 104 kilojoules per mole in that outcome for that. So it's just like I say, jot down the data, plug it into the formula, and solve for whatever the problem's asking you for. So let's say we're given in this reaction delta EA now is 104 kilojoules per mole. R value 0.008314 kilojoules per mole Kelvin. K1 is, we can use that one, or K2, it doesn't matter, is 1.4 times 10 to the minus 4 seconds to the minus 1 at T1 to equal, well, I'll do it over here. T1 equals 308 Kelvin. And so we're looking for K3, we'll put it in there as that, is the unknown at T3 to equal 55 degrees C, and that's 318, 328 Kelvin. So there's a plug and chug in that. But in the substitutions, you're looking at working for here K3 over K1. So you've got to solve for this term right here. Well, the ratio of a logarithm is ln K3 minus ln of K1, and then all the rest of the formula from there. And so what I would do is, add ln of K1 to both sides, if you remember this from your algebra. So it's ln of K3 to equal ln of K1, make that look like a 1 anyway, plus delta EA over R, T2 minus, T3 this time, 3 minus T1 over T1 times T3. And so you have everything over here. Now when you get the value for the substitutions, then you have to take the analog, which is an E function. K3 is E to whatever the value is that you find right there. So this is a very straightforward and direct problem. It's specific, but you are going to see that kind of problem come test day. So I'm going to leave it there so I can move on to the background on the lab. Give it a try, and if you have problems, certainly send me a note and I'll scribble it out in more detail.